Okay, our second talk of the day is from Evan Mcdonough, and Evan will tell us about the Gravitino Swampland Conjecture. Take it away, Evan.
Thanks, Cody and John, for inviting me. I'm happy to be here. I'm happy to be speaking to this audience of experts. There's exciting work that I did recently with Rocky Kolb and Andrew Long. Rocky at University of Chicago, of course, and Andrew is new faculty at Rice University in Houston. And these days I'm a Calvi Fellow and a Rico Framing Fellow at U Chicago. And so this is based on these two papers. Right. So the starting point for today, of course, along with many of these talks relating to the Swampland program, and the Swampland program certainly needs no introduction to this audience. But I'm particularly interested in this interplay between quantum gravity and our universe, meaning what can quantum gravity teach us about the universe, help us explain phenomena that we observe, and what can the phenomena that we observe tell us about the structure of quantum gravity. And as a baby step in the direction of quantum gravity, we have supergravity. And ostensibly what supergravity gives us on top of, say, global supersymmetry is the gravitino. So understanding where does the gravitino fit into this picture. And the particular playground I'm going to be considering is this phenomenon of particle production in cosmological spacetimes and looking at production of gravitinos. And from there, it leads into what we're referring to as the Gravitino Swampland Conjecture. Right, so first things first is the landscape program. And in case anyone's been living under a rock, the Swampland program is to try and understand this mapping from quantum gravity to the actual space of theories, which are four-dimensional models, which sit inside the vacua of string theory, say the landscape. So, I mean, so at a practical level, what models that people build, so from what describe particle physics inflation, what subset of those models actually correspond to the vacua of string theory? And in particular, what I'm going to be talking about today is going beyond thinking about just, much of the Swampland program has been focused on things like axion inflation and what can be the axion decay constant and what are the implications of that for natural inflation. Here I'm going to be looking at supergravity models and what can we say about which supergravity models have some embedding a UV completion into quantum gravity. In the context of the leading candidate for quantum gravity string theory, we have this hierarchy of energy scales here, where we think we have some world sheet description at highest energies, and we have the string scale, and in the alpha prime expansion, we get out our supergravity theory. We compactify, and there's some energy scale separating 10D from 4D, which is the Kluge-Klein scale, and we get out some 4D, usually n equals 1, d equals 4, supergravity theory. And it's in this context that we usually try to understand phenomena like moduli stabilization, and quite often the construction of de Sitter solutions. Well, there's been fantastic work on understanding de Sitter from 10D, which is a subject for another talk. So suffice it to say, what I'm interested in today is how can we sort of trim down the space of 4D supergravity models and understand, in this huge space of models that people build, which models in particular are actually in the landscape. And the playground for this is cosmology. And this has really taken off in the last few years, in particular with the cosmological collider physics research program. And the reason for excitement here is that the leading cosmological paradigm is that quantum fluctuations in the early universe make up everything around us today. So the paradigm of inflation says like quantum vacuum fluctuations, you can see the horizon during inflation. They're stretched by the expansion of the universe, and those form the seeds of structure. The large-scale structure of the universe and everything around us, but the seeds of that were these quantum vacuum fluctuations. Of course, these are nicely imprinted on the CMB, which we've measured to exquisite precision. Now, this picture of doing particle physics with cosmology is that these quantum vacuum fluctuations, before we observe them today, could have undergone many scattering events with every possible field that's coupled to gravity even. And I should mention that particularly there's been a lot of action on this front with understanding higher spin fields, because we think we have a good grasp of higher spin fields in de Sitter space, so you can understand the interactions and the scattering amplitudes and the signatures, particularly in non-Gaussianity of higher spin fields. The aspect that I'm particularly going to be focused on today is this phenomenon as inflation as a particle factory, but not just a cosmological collider, but also a way to produce particles. And the basic idea here is that the expansion of space during inflation converts your Bunch-Davies initial condition imposed inside the horizon into, for example, here with if you have a field that has a mass bigger than Hubble, you get a Hankel function and some exponential Boltzmann suppression. And how you interpret this from when you map this onto the post-inflation vacuum, say in the matter and radiation dominated era, you realize that you've gone from a positive frequency mode to the positive and negative frequency modes of the vacuum state as defined by this post-inflationary era. And the coefficient of this negative frequency mode, we call this the Bogoliubov coefficient. And this is your operational definition of what it means to have particles with respect to your vacuum. And most famously, this is how you derive Hawking radiation. And how you can qualitatively understand how is it that you went from a vacuum state during inflation to having some particles afterwards, is the idea that the vacuum state of your quantum field theory is changing non-adiabatically. So for example, this is we call this this is how you diagnose adiabaticity, is how the time derivative of the dispersion relation divided by the dispersion relation. And you can see for some field with mass m, it's peaked roughly when k over a is equal to mh. And I should mention that the most dramatic effect actually happens right at the end of inflation, so in this oscillatory phase. And this has been its own huge research program, largely started by Rocky, starting with WIMP-Zillas, understanding the production of dark matter through this sort of particle production events happening at the end of inflation. So where quantum gravity enters into this, and members of this audience have studied this extensively, is what we believe to be the UV sensitivity of models of inflation. And in particular, in large field inflation, which is, as a class of models, extremely nice because it's an attractor in phase space. Related to this question of eternal inflation is the phenomenon of being an attractor, meaning if you have some n² phi² potential, you can start up as high as you want with any velocity you want. Hubble friction will slow you down and you enter a slow roll inflation phase. But the basic premise of this is that you're undergoing Planckian field excursions, which itself has its whole swampland story. And if you're undergoing Planckian field excursions, then Planck suppressed corrections to the potential aren't suppressed at all. So the natural way to get around this is to introduce a shift symmetry. This enters into axion models, of which there are two classes. One, natural inflation. Unfortunately, this is conflict with weak gravity conjecture, and I should mention that John actually has some really interesting work recently on how to understand this and the breakdown of this non-expansion for super Planckian decay constants. And the other class of models is monodromy models. And in this class, and sometimes it's been argued that it leads to flattening, but generically you have some problems with back reaction, which again, members of the audience have worked on extensively. And the basic idea here is that you have a Gauss law constraint in your internal space. So if you have, for example, some world volume fluxes on your brain are decreasing by a huge amount, this implies that, for example, D3 brains are secretly moving off of your D5. You're shuffling around the charges in your internal space, and to a huge extent, if you're undergoing a Planckian field excursion. So this motivates, this UV sensitivity motivates understanding and building UV complete models. And the baby step in the direction of doing this is to construct cosmological models in the context of supergravity. And in what's referred to these days as textbook supergravity, the textbook being the fantastic book by Freeman and Van Proyen. The description here of supergravity is to promote your graviton into a gravity into a graviton and a gravitino, where you went from global, for example, to local SUSY transformations, which is the gauge transformation of the gravitino. And your scalar fields phi I, for example, your inflaton gets promoted to the scalar component, which is a complex scalar of a chiral superfield. And the action for the scalar field is specified by some scalar potential and superpotential. And in SUSY breaking backgrounds, we have the Einstein super Higgs mechanism where the gravitino eats the gravitino and gets the mass. And sorry if this is all too simple of a review. I just want to make sure we're all on the same page and be thorough. So one of the biggest breakthroughs to happen in supergravity happened a few years ago, which is the construction of an intrinsically de Sitter supergravity theory, referred to as pure de Sitter supergravity, which is a supergravity theory wherein the vacuum, the ground state of the theory spontaneously breaks local supersymmetry, and so supersymmetry is non-linearly realized. And the basic construction of this theory is to take the textbook sugra and you take some superfield S, which satisfies a nilpotency constraint in superspace. And when you solve this equation at order by order in the fermionic coordinate on superspace, you find this non-trivial solution where the scalar component is related to the fermionic component and the auxiliary field. And when you plug this back in textbook sugra, you get out pure de Sitter sugra. And it's called pure de Sitter because when you go to unitary gauge, it just describes just the graviton and a massive gravitino propagating in de Sitter space. And there's been a ton of fantastic work connecting this to string theory, which I don't have time to go into today, but I just mentioned that a lot of this work is done by Tim, I saw it in the audience, and along with Renata and Gabriel as well. There's a ton of fantastic work here understanding of this nilpotency constraint comes from an NGD3 brane and a flux compactification, and then also how you get a more general constraints like an orthogonality constraint when you consider an NGD3 brane that's allowed to move in your flux compactification. Right. So one of the reasons why this de Sitter supergravity really took off is that it's very simple to build cosmological models. And here I'm going to look at a simple class of examples that were developed in these two papers. And I should mention that there's many, many papers on building cosmological models in this context. And the reason why it's simple is that if you take this field S, the most general superpotential you can write down, because it squares to 0, is linear in S. And the usual recipe, the modern recipe for building supergravity models of cosmology is you take some scalar potential, which has a shift symmetry for some component of your complex scalar, and that shift symmetry is broken by some small correction. So for example, here, this is a perfectly fine supergravity model of a chiral superfield T, where there's a rescaling symmetry of that field T. So if I take, so the radial component then of this field has a shift symmetry. And this type of scalar potential is naturally gives you out alpha attractors. There's been a ton of work on the phenomenology of these. And the idea of these two papers is that if you take a small correction to the scalar potential, which breaks the shift symmetry, so here, again, the shift symmetry of the radial component, it's a rescaling of this field, you naturally get out inflation and you get out your cosmological constant. And this has some particularly interesting features. One, in this simple setup, the SUSY breaking is always at all times orthogonal to the cosmological evolution. We say SUSY is broken by S and not by the inflaton, which is contrary to the usual expectations. Two, the gravitino mass is a constant, and that follows from the fact that W has no dependence on the inflaton, and K itself is constant during inflation. But in fact, and the last interesting feature here is that the inflatino mass, which is the fermionic component to T, is actually tunable. And so, for example, depending on what is phi at the end of inflation, it could be hierarchically larger than the gravitino mass. And this gives you a particularly simple model for the gravitino, which I'll talk about in a second. And one connection I'd like to mention, which hasn't been fully explored, but I think particularly in the placing this in the context of the swampland would be interesting, is these first two phenomena of that SUSY breaking is orthogonal and you have mass gravitino comes from the fact that after you impose the nilpotency constraint in superspace, the effective Kähler potential you get out for T has this unbroken global U1 symmetry. So that's an interesting thing I'd like to talk about more and maybe understand more by talking to this audience. Right. So let's get to the gravitino. And I'm going to work in a particularly simple case where the inflatino is heavy at the end of inflation. I'm going to look at quadratic order in the gravitino field. And so these, treating the inflatino as heavy is, this is the model that you get out in sort of a few different separate classes of supergravity models. And I mean, if you look in the supergravity literature, it certainly seems like the sky's the limit. So if you can think of it, it is out there. Now, if you take this Lagrangian and you do a lot of nitty-gritty calculations to split your massive gravitino into the 3/2 and 1/2 helicity states, the interesting phenomenon that you find out, and it's been known since the late 90s, is that the helicity 1/2 states, the longitudinal mode of the massive gravitino, has a non-trivial dispersion relation. And so if you split this into plus and minus helicity states and you look at the dispersion relation for those particles, what you have here is a non-trivial, differing from 1 sound speed, which is somewhat familiar from inflationary cosmology, and we can talk about that connection more. And this sound speed here is determined by the background evolution with the Ricci scalar, Hubble constant, the mass of the field, and also the time dependence of the mass of the gravitino. So in n equals 1, g equals 4 supergravity, there's a particularly simple expression for the sound speed and a geometric interpretation for it, which has to do with vectors on field space. So if you take a set of n chiral superfields, so you have a field space manifold, which has n complex directions, you can, the SUSY breaking itself corresponds to some vector on field space saying in what fields are breaking SUSY, and the cosmological evolution is also specified by a vector on field space. And the maximal deviation of CS from 1 comes from when these two things are orthogonal, the SUSY breaking and the cosmological evolution. And that is exactly what is the case in that these simple classes of nilpotent models that I discussed before. And this phenomenon of CS differing from 1 has been called the slow gravitino. And I should mention, so you could work out nicely just from maybe you're good at mental math, that CS squared is bounded between 0 and 1. Right, and I'll try not to go over time here. So I'll speed up a little bit. So the fascinating feature which prompted this work was the observation that the gravitino sound speed can vanish. So for example, if I take a constant mass gravitino, which is the case in a lot of supergravity models, and in that case, it's indistinguishable from the massive Rho-Rita-Schwinger model. And I take some FRW spacetime, so by some equation of state, sound speed is given by this. And if I take an initial condition that the mass is less than the Hubble constant, say I have some radiation dominated universe. This is the standard Big Bang cosmology of the 1960s. At some finite point in the future, the sound speed will vanish. Which means you have some radiation dominated universe. H is redshifting. As WH passes through M, the sound speed vanishes. And now if we look at the context of inflation, what you find is as the mass falls below the Hubble expansion rate at the end of inflation, you get a zero touching of the sound speed, and then you get many, many, many zero touching as you get down to smaller masses. And we think we have a really good handle on quantum fluctuations during and after inflation, which is this whole research program of the cosmological collider physics. Is Rocky's research program of understanding gravitational production of dark matter and inflation, getting back to this from Scylla's. So what happens in this type of background? So the first point I'd like to emphasize is that if you look at the vacuum state of these two Dirac equations that specify the helicity states of the gravitino, and for your helicity 1/2 gravitino, you have this non-trivial sound speed, and you come back to this abaticity condition I mentioned before, where when adiabaticity is violated, you have this production of particles. The usual behavior is that this quantity always goes to 0 at large k, just because omega k squared is going to infinity. It costs a lot of energy to make a high momentum particle. But if you compute this and evaluate it at vanishing sound speed, it becomes independent of k and is the ratio of h over m. And so if you recall, the sound speed vanishes if m is less than h, so this implies that at all those times abaticity is violated. Now I'm going to get into some numerical results, and to do that, first we need to touch just upon some of the technical details, which maybe in light of time aren't super important. You can look at the paper, but suffice it to say, you split into the plus or minus helicity states. You have rather complicated gradients of motion, and what you want to construct is the asymptotic behavior of the negative frequency modes, from which you construct the Bogomolov coefficients, and from this you can compute the spectrum, which is the number, the co-moving number density of particles. And the picture in 1999, when people were numerically studying just single car superfield models, is that you have some production of particles which peaked at some value of k, and then as you go to higher k, you get these fast oscillations, which essentially is just coming from the fact that the perturbations are probing the oscillations of the background. And the single car superfield case, from this geometrical picture, two vectors in a one-dimensional field space are always orthogonal, so the sound speed is identically equal to 1. You can prove this in a number of different ways. So now let's get to this, the gravitino at the end of inflation, and the phenomenon that we uncovered is this, what we've referred to as catastrophic production. Where on the left here, we're looking at the growth of the Bogomolov coefficients at the end of inflation for differing values of k. And what you see is this synchronized growth for all these values of k, all happening shortly after the end of inflation. And then if you translate this, you take the asymptotics and translate it into this number density, what you find is instead of the rise and then fall fast oscillations, what you have is rise and continue rising, you fast oscillations, and you can continue it off and off this page, and it continues rising for the helicity 1/2 component. In this case, where the mass is less than Hubble, and this is where you have these many zero touchings of the sound speed. And as you dial up the mass past the mass of h at the end of inflation, so that the sound speed never vanishes, this production is tame. You get back to what you would expect. And incidentally, this is ties in nicely to this research program studying dark matter production from inflation. And this is work that's in progress right now. But I'll put that aside for today. And so what are we to make of this, that you're producing particles of arbitrarily high momentum and some subset of supergravity models? And what we would argue is that this is leading to, or implies rather, a breakdown of the effective field theory. So for example, if I consider some tower of operators and they're suppressed by the cutoff, which is the cutoff of your supergravity models, where there's some corrections when quantum gravity should kick in, and you know that these operators have to come with the gravitino mass, if insofar as the gravitino mass is still the order parameter for the breaking of the spin 3/2 gauge invariance. And let's say they're suppressed by n powers of the cutoff, and you have n derivatives. If you produce a particle k with momentum lambda, you have this infinite tower of operators, which will contribute to the dynamics. But more generally, just what is the physical picture of Wilsonian effective field theory? Is that if you produce a particle that is able to probe those length scales, which you've ostensibly integrated out, then your effective field theory is no longer effective. And I can get into this more, but this is qualitatively different from the gravitino problem in that it's not an inconvenience, it's not an observational thing where we observe the universe as not being totally dominated by gravitinos, but it's more a consistency problem with, you started with what you thought was a consistent effective field theory, and then without warning, you get this breakdown for a certain region of parameter space. So this leads us to what we've called the Gravitino Swampland Conjecture, which is essentially a statement that this can never happen. So in more words, the statement that the gravitino sounds continuously positive definite in all 40 effective field theories that are low energy limits of quantum gravity. And to be slightly more technical, in principle, you can have a matrix of sound speeds relating different spin half components, and the determinant of this matrix of sound speeds needs to be positive. Now, the conservative interpretation of this is simply that supergravity models which violate this are incomplete. And so you can toss in some arbitrarily small correction and lift a vanishing of the sound speed to some arbitrarily small non-vanishing of the sound speed. And in this sense, it's analogous to the no global symmetries law of quantum gravity. You could toss in some small breaking of the global symmetry, and in principle, great, it no longer has a global symmetry. So this is a non-vanishing statement. So in that sense, it's near trivial to satisfy. But in fact, if we look at the history of no global symmetries argument, leading to, for example, the weak gravity conjecture, it seems like this might be an interesting rabbit hole to go down, this Gravitino Swampland conjecture. So, all right, let me wrap up here, and this is actually perfect timing. The summary that I think the starting point here, and maybe I didn't take long enough time to convince you, or maybe you're all already on board, is I think cosmology is a great playground for stress testing theories. This is something that I'm extremely interested in. Recently has become the phenomenon of studying higher spin field theories, which I'm really excited about. And then also testing supergravity theories, and of course, models of inflation and string theory. And if you look at these supergravity models and ask, well, what are they really giving us as, what do they give cosmologists? Let's say, is this phenomenon of, de Sitter space breaks over symmetry, or gravitino is massive, and a massive gravitino has a modified dispersion relation, and this sound speed can vanish. And this can happen in many supergravity models. And I should mention there's many supergravity models where this doesn't happen. There's some supergravity models where this does happen. And when the sound speed does vanish, you can have huge production of fluctuations of high K particles, because it's essentially produced for free. And the GSC is a statement that this can happen. And what would be exciting, and this is speculation with zero evidence, but perhaps inspired by other swampland conjectures, is that perhaps there could be a strong version of the GSC, which is that the sound speed is bounded by some order 1 number. And that's all I want. Well, let me, in light of time, just say thanks.
Okay, thank you, Evan, for the very nice talk. Let us all thank Evan with our clap emojis. Are there any questions for Evan? Looks like we have a hand raised from Cooper.
Yes, can you hear me, Evan?
Right, yeah.
Yeah, thanks. That was an excellent talk. So from your Gravitino Swampland Conjecture paper, it looks like you have a bound on the scale of inflation being bounded by the gravitino mass. And this is a sort of new way of looking at the old Kalush-Linde problem, where in order not to decompactify extra dimensions,
right,
you have the same bound there. And over the years, there have been some ways to get around it. There was a paper by Shamit about 10 years ago where he had a model that did that. And then also Kalush-Linde introduced racetrack potential, superpotentials, which, so I guess my question is, do those models that evade the Kalush-Linde problem actually, do they belong to the swampland, or do they belong to the landscape?
Well, let me back up for a second and mention that one of the spectacular achievements of the last couple of years has been, and this is work by Liam McAllister and collaborators and people on this call, actually finding points in the landscape that have the small W naught necessary to get KKLT. Now, when you go from KKLT to the, these racetrack potentials, you have to introduce this new fine tuning of W naught with, now you have two exponents and two coefficients and W naught that need to satisfy certain fine tuning in order to construct this, this solution. And whether or not that fine tuning is possible in the landscape, I think is a totally open question. Now, with regards to, is it in contradiction with the Gravitino Swampland conjecture? So what I mentioned about it being a simple non-vanishing condition, and we have a section on this in our paper. I mean, the fact that, I'm not screen sharing, one second. Right, if you just introduce some perturbative corrections to the Kähler potential, which generate a time dependence to the gravitino mass, then the sound speed becomes small but non-zero. So in that sense, you could say the models are just incomplete, and if you include perturbative corrections, it's fine. And that begs the question, well, how big do these perturbative corrections have to be? And say in the landscape, can we say something about what's the minimum of the sound speed? So I would say in terms of models that people have, like the racetrack, for example, that would violate the GSC for certain supergravity implementations, all you need to do is introduce these small corrections, and now the sound speed doesn't vanish. And now what do you do with that information, I think is, let's say, left for future work.
Okay, thanks.
Oh, we can't hear you, Cody.
David, is your hand raised as well?
Yes, thanks. Thanks, Evan, for the nice work and the nice talk. I had a related question. So if I understood correctly, this non-vanishing of CS, even though you may call it trivial, actually translates into this inequality of the ratio of M over H, which may seem a little less trivial in a sense. And so my first question is whether this is correct. And my second question is, in case there is a stronger version, as you suggested, with some non-zero coefficients, would this non-zero number appear in this ratio of M over H, basically, in the inequality there?
Right. So okay, let me, I can share, sorry. So you're saying here, so this is just straight up take time derivative of this, set CS equal to 0, and this is what you get. So is it, okay, and then the connection to, so why does M over H lead to vanishing sound speed? I don't have the simple expression here, but if the 0th order condition, let me say, is that the gravitino mass needs to be a constant. And then in order for this whole thing to vanish, you need that H, or this combination of H and the Ricci scalar, needs to be able to cancel with M. So this is this connection between the background cosmology and the mass. So when in the cases of the gravitino mass is constant, you can have this non-trivial cancellation between the background and the mass. And then this expression here is just totally general, the dispersion relation evaluated at vanishing sound speed. But wait, I think there was a second part to your question that I'm forgetting.
Yeah, thanks. Yeah, the second part was, in case there is a stronger version where the speed of sound is bigger than a certain number, whether this would modify a H over M bigger than 1.
Right. So it would regulate this, right?
Right.
So if CS was, I mean, now if CS was arbitrarily small, like say, as CS goes to 1 over infinity, if K goes to infinity faster than CS goes to 0, say, then this gets regulated for the K equals infinity mode. And then, so you need to ask for your cutoff, if the K mode at the cutoff is undergo non-adiabatic evolution, and then so you can say, basically, CS needs to be less than 1 over the cutoff in order to get the catastrophe. So if CS is bigger than 1 over the cutoff, then at least the cutoff itself isn't non-adiabatic. These, I would say that should strictly be a much, much less than but you can treat all these as like less than squigglies.
Thank you.
And we have time for one more question from Kerman.
Thank you. Very nice talk, Evan. Just want to make sure if I understand correctly and whether the interpretation of your conjecture in a different form is the way you can think about it as well. So basically, if I understand, you're saying that in the models where supergravity, supersymmetry is broken, you have to have a gravitino mass which is not too small. Mass is bigger than h, basically is the statement, right?
In simple models, you can engineer models where the gravitino mass is small and varying rapidly with time, and then you will be fine. So that simple interpretation, which I like.
Okay, so let's take this.
There are model building exceptions to that.
Okay, let's talk about the simple version. So in that version, basically saying if supersymmetry is broken, the mass associated with that mode, the gravitino, should be bigger than h. Let's take that view.
Right.
The modified version of the conjecture,
right.
Some version of the conjecture. In some sense, that is close to being interpretable in a different way, which makes it very plausible, in some sense unavoidable, by just saying that if a mass of anything is less than h, you cannot measure it. So in a universe which has a Hubble scale h, you cannot measure masses in any physical way if it's less than h, in which case any mass in between 0 and h should be viewed as 0 because you cannot measure it. And therefore,
well, who is measuring it and when are they measuring it? Because h today is 10 to the minus 33 electron volts.
Well, I'm not talking about the varying h or anything. I'm just talking about an idealized situation where you have an h, constant h. So in that situation, you have a situation where you cannot even measure m. And therefore, it's consistent with saying supersymmetry is not broken. So in a sense, you could say two things. Either supersymmetry is not broken, in which m is 0, or supersymmetry is broken, in which m has to be bigger than, should be measurable, in which case m should be bigger than h. So in some sense, it makes it very plausible what you're saying, at least in that setup.
Yeah, I think that makes sense. The only part that I'm unsure about is who is the person doing the observation.
Well, that's precisely the point. If m is less than h, nobody can do the observation. That's the whole point. So it's not a physical question. The only thing you can do if m is bigger than h. So you cannot determine if supersymmetry is broken if m is less than h. So I might as well call it unbroken then.
Yeah, I think that's a really interesting way to view it.
But so I agree, it's very plausible from that perspective. Thank you.
Okay, and with that, thanks, Evan, again, and let us thank both of our speakers today for the very nice talks.